Hello and welcome to College Physics 1, Lecture 26, Impulse and Momentum. Our previous three lectures focused on rotational motion, but here we start to shift gears again. For the next two lectures, we're going to focus primarily on the concept of momentum, how it relates to impulse, even how it relates to Newton's second law, and then we're going to talk about how momentum is conserved. So this is kind of a new unit of our course where we start getting into conservation laws, really important concepts, enough so that they're considered laws that carry us into kind of a new section of physics. So this is almost like a segueing topic for us. What's really cool though about this material is that it stems from old material. There's not really anything new here. We're just looking at older material in a different way. So let's jump right into this. First of all, when we talk about impulse and momentum, we're talking about what happens during collisions. By definition, a collision is just a brief interaction between objects. And it doesn't have to be two, it could be more than two objects colliding at the same time. But what happens during a collision is the objects that are experiencing an effect due to the collision, the ones that are interacting, those objects will take some time to compress and then expand back to their shape. Even if the object is pretty solid, it will still compress, just much less than a more flexible object like you see in the pictures on the right, in which a soccer ball is being kicked. So, what's unique about this material now is that we're going to be thinking of a force that changes over a short duration of time. This force is often quite large, but it changes. So, in the past, everything we've been looking at is just a single force. It's the force that you push an object with, or the force of weight. It's just a single value. But now we realize that in the real world, things are of course more complex than that. So, we're talking about a changing force. We call this an impulse force. It's a very strong but quick force delivered to an object during the event of a collision. And when we say short duration, we're talking milliseconds, fractions of a second. So this graph here shows you an example of the force versus time when you kick a ball or, really any collision. What happens is your object is going to start to compress. So as your object starts to compress in this very short time frame of a collision, the force that your object experiences is going to increase. So we see this increase up along the graph. Well, eventually your object will reach its maximum compression up at the top. At which point, the object starts to expand again and start to decrease its force until the contact between the two objects ends. So this impulse force increases and then decreases based on how flexible the object is, in other words, how able it is to be compressed. Well, if we want to figure out this concept of impulse, or the term impulse, we define it as the area under the force versus under the force versus time graph. So whatever this area is what we call impulse, represented by the letter J. Note, we already used I for moment of inertia, so we just go to the next letter in the alphabet, which is J. So the area of this region underneath our force versus time graph is the impulse. Now, that's great. I mean, we have a way to define it, but if you have been doing anything in this class or following along with this class, you'd recognize that this is a curve. We've never taken the area of a curve in our class because that would require integral calculus. This is not a calc-based version of physics. This is an algebra-based version of physics. So, either we can't take the area of this because it's curved, or we can simplify it. And we've been doing that the entire time. Why not simplify this graph to make it work for us? So instead of thinking of this in terms of a force that's constantly changing and making a curve in the graph, why don't we consider an average force, a constant valued force that has the same duration as the actual force. So here is our complicated curve again. It has some duration, right? It takes some amount of time. Well, why not just make a force that has an average value for that same amount of time. So this graph on the bottom right shows us that average force. We simplify the shape from a curve to a rectangle such that it has the same area. In doing so, we can actually have a very simple equation for the area. So we said impulse is the area under the force curve. Well, notice the area of this rectangle now is F average times delta t, length times width. So you pull that together, and we now have an equation for us to be able to use to determine the impulse. So, by definition, impulse is your average force times time, or the area under the curve. Sometimes it will be a common shape that you can take the area of. It could be a rectangle, it could be a triangle. You can take the areas of those, but not if it's curved. So looking at this equation here, we should see that we have a new term, impulse, which means we're going to have new units. We measure force in units of newtons. We measure time in the base unit of seconds. So the unit of impulse is a newton second. But keep in mind that a newton is a kilogram meter per second squared. So we can also write this if we have a second up top and 2 seconds underneath, that cancels out, leaving behind a kilogram meter per second. This is the preferred unit to use when discussing impulse. Now, it seems kind of weird, like why would we choose the unit that looks more confusing, right? It's a kilogram meter per second instead of just saying newton seconds. Well, we're choosing to do this for a reason you'll understand in just a few minutes when we talk about momentum. So just take my word for it for now that it makes sense to actually choose kilogram meter per second as our preferred unit. As our preferred unit here for impulse. Now, one thing to make a note of before we move forward. This is technically a vector equation. In fact, I probably should have put my arrows in. Impulse is a vector. Force is a vector. So based on this equation, if F and J are directly proportional in this case, they're pointing in the same direction. So the impulse is delivered in the direction of the average force. So these do have directions, just to be clear. Okay. Well, right away, since we have come up with an equation for impulse, let's get practice with it. Let's hop right into solving an example. This brings us to example 1 of lecture 26. It says that a rubber ball experiences the force shown as it bounces off the floor. It asks, what are the impulse, we'll say part A, so A, what is the impulse, and B, the average force on the ball. Okay. Well, we are given a graph, and the first thing we want to do is realize, okay, like it wants us to solve for impulse J, right? We have two ways to solve for impulse, right? If you look at our equation here, it's either the area under the graph or F average times delta t. Now, we are given a time, right? We are given 8 milliseconds. We're also given a force. But be very careful. Because you see a force and a time, and you know the equation is F average delta t, it is often the thought of a student to take those two values, multiply them, and get your answer. But this is not the average force. That is the max force. This is a constantly changing force. I mean, look at that graph. It's increasing and then decreasing. That is not the average force. That is the maximum force. So we cannot use F average delta t to solve. We have to use the area of the force graph in order to solve. So in this case, it is not a curve. It's actually a common shape. So we can take the area of this. We know it is a triangle And we know the area of a triangle is 1/2 base times height. So we just take 1/2 base times height and try to solve. In this case, we have 1/2. The base is the duration, 8 milliseconds. That's either, you can write this in one of two ways. Milli is 1/1000th of a second, so you'd have to move your decimal place over 3 times. So you can write this as 0.008 or 8 times 10 to the minus 3. I suppose I'll just write it as 0.008 seconds. The height of this triangle is that max force, 300 newtons. So this works out to be 1.2 kilogram meters per second. That is our impulse. Now again, if you don't like the units, if you look at the equation, you have newtons and seconds. If you write your answer with those units of newtons and seconds, that's totally fine. There is nothing wrong with that. Just note that I choose to use kilogram meters per second, as I talked about earlier, for a good reason that I just haven't disclosed yet. That's part A. Part B then asks us to figure out that average force. Right now we're looking for F average. Well, we really only have one way to figure that out. From our equation, F average is right there. Impulse J is equal to F average delta T. So let's work with that equation and solve. J equals F average times delta T. So if we're looking to solve for F average, that would simply be the impulse J over the time interval delta T. We do know both of these numbers. We solve for the impulse in the first part, and the time is given to us, so we can solve directly. 1.2 kilogram meters per second divided by the time, which was that 8 milliseconds, or 0.008 seconds. This comes out to be 150 newtons. And there you have it. You are able to solve for both the impulse J and the average force through this process. Now, this equation that we've been applying, J equals the area, which equals F average delta T, we just used it, but we're going to expand on it a little bit further and kind of work with a similar version of it in future problems. So, this is impulse. But the reason we really brought this up is to get us to our next topic. The equation that we have here, J equals the area under the force curve, is extremely important. But even more important is the concept of momentum. So when you deliver a force to an object in a collision, so that could be you kicking the soccer ball, it can be you hitting a puck with a hockey stick, it could be 2 cars in a collision. The force, or the impulse force in this case, that's delivered to the object, by definition alters its velocity. This is just F equals ma. By definition, if you apply a force to something, you are going to cause the object to accelerate. That's just Newton's second law. We've been dealing with that for weeks and weeks in my class or through numerous lectures in these series of videos. Acceleration, by definition, is a change in velocity, delta v over delta t. So we're expanding the equation, and by definition, delta means delta means final minus initial. So all we've done is taken Newton's second law, F equals ma, and expanded it to be m times delta v over delta t. Well, now, even though this so far, the white equation at the top here, that is Newton's second law. We haven't done anything new. So all we're going to do is take that delta t and multiply it over to the other side. In doing so, we come up with a quote-unquote new equation. F average delta t is equal to mv final minus mv initial. This is a very important equation. First of all, it should look somewhat familiar to you. And to be clear, this is still Newton's second law. We just wrote it in a weird way. The left-hand side of this equation, we just defined what this is. We just said F average delta t is the impulse So the left-hand side of that equation, by definition, is impulse. But the right-hand side of the equation is something new. On the right-hand side of the equation, we have mv final minus mv initial. That is the change in mv. We define mv as the momentum of the object. We can't use m for momentum because we use m for mass, so we use the letter p for momentum. So we are defining this. We are saying, by definition, momentum is mass times velocity. Extremely important. So the left-hand side of the equation is impulse. The right-hand side of the equation is momentum, change. Let's look at units. As we always do when we have a new quantity, we have to analyze what the units are. Well, we have mass, which we use kilograms for, and then we have a velocity, which is measured in meters per second. So those are the units of momentum, a kilogram meter per second. That should look familiar. A kilogram meter per second. Well, look at here. This is why I was emphasizing earlier that a kilogram meter per second is the preferred unit for impulse. The reason we choose the slightly longer looking unit here for impulse is because this is the same units. I can't type. Same units. You can barely read that. Same units as momentum. Same units as momentum. So that is why we chose to use kilogram meters per second instead of Newton seconds. It's consistent throughout our work. So with that said, we also want to make note of the fact that we did put arrows above these. Momentum is a vector. Just like velocity v is a vector, they have a direction. Very similar to how we defined impulse. We said impulse is a vector that points in the direction of the average force. Momentum is also a vector that points in the direction of velocity. So, just for the sake of knowledge, this isn't a table that students have to memorize. It's not even one that you have to reference to solve problems. I just threw this in here because I thought it was interesting. This just shows you some random objects and what their momentum on average would be. So remember that momentum is just mass times velocity. So if you have a small mass and a small velocity, you can have a really small momentum, such as that of a falling raindrop. A raindrop's mass is very small, and its speed is also pretty small, so it's going to have a really small momentum. In this case, we have 10 to the minus 4. But for a car on the highway, here we're talking about a very massive object, also at a high speed, so it's going to have a really big momentum. In this case, 30,000. So I really put this in here just to give you some perspective. If you were to try to calculate the momentum of a falling raindrop and you get 30,000 for that, either that is like the world's largest raindrop, or it is moving so incredibly fast that we probably have some concerns. So this at least gives you some ballpark ideas on what kind of values you could be expecting for momentum. So it's just a helpful reference, perhaps, in case you ever need it, to kind of question whether or not a value you get when you're calculating a momentum makes any physical sense. All right. Well, that big equation we had on the previous slide, F average delta T equals mv final minus mv initial, is actually more important than it seems. If you look at that, remember we said the left-hand side of this equation is the impulse J. We also said that P equals mv. So mv final becomes P final, mv initial becomes P initial, and suddenly we're starting to see that this equation can be written in a much more simple way. Rather than saying F average delta T equals mv final minus mv initial, F average delta T is impulse, mv final minus mv initial is a change in momentum. So that equation is just J equals delta P in the shortest way of writing it. Well, this is very important. It even has its own name. This is called the impulse momentum theorem. Impulse momentum theorem because it is an impulse and a momentum. Big surprise. So this tells you that if you apply an impulse, J, to an object, you deliver an impulse, you are going to change its momentum. So this is a very important equation. If you are in my class watching this video, the current homework that you have, I guess it might vary from year to year, but about half of my students' current homework will use this equation. So it's a very important one that is applied in numerous ways. Now looking at this, if you take the equation and rewrite it for the average force, you can write it as delta P over delta T. I mean, I have this down at the bottom of the slide, but I wanted to write it bigger just for emphasis. This is actually a really, really, really important result in the real world. Because what this is saying is that if you can increase the time, delta T, you are going to be, if you look at the equation, you are going to be dividing by more, right? If you make, because delta T is in the denominator, it's below the fraction, right? So if you increase your delta T value, the time of collision, you are going to decrease your average force. So we're saying that if you increase the time of a collision, you can decrease the force that you experience during that collision. Think about the implications of that. There's actually many. In fact, I'm going to skip our example and just hop right to some examples real quick. Hedgehogs. Didn't see that one coming. Hedgehogs have a problem of falling out of trees. They have a spiny back that protects them from predators, but it also helps them take less impact when they fall out of a tree. When they do so, they curl into a ball and fall toward the ground back first. They do so because that means they will land on the cushiony spines on their back instead of like their little noggin. The reason for this, again, comes from that equation we just wrote. F average equals delta P over delta T. What's happening here is by falling on its cushioned spines, it takes more time to collide with the ground, more time to slow down and be cushioned in its fall. So you're increasing the value in the denominator, meaning you're dividing by more, making your average force smaller. So this hedgehog, I'm assuming, doesn't understand the impulse momentum theorem, but it does know to fall on its back so that its fall is cushioned and increases the time it takes to collide with the ground. Another great example of this is catching water balloons, or in this kid's case, not catching water balloons, unless you consider catching with your face successful. Anyways, the point is, if you've ever had a lot of experience with water balloon fights or anything like that, if you quickly reach out and try to grab the balloon in front of you, it's probably going to burst over your hand and then just cover you in water. Because you reached out and tried to grab the balloon, meaning the balloon is interacting with your hand for a very small amount of time. But if you can follow through and catch the balloon, moving your hands backward with its motion, so, the water balloon's coming in at you, you try to grab it, and you bring your hands down with it, you're increasing the amount of time that the balloon is colliding with your hands, thus decreasing the force you deliver to the balloon, and hence perhaps allowing it to not pop. So again, very, very important. So this brings us to example 26.2, our second example. This is a great one to cover. I really enjoy doing this one, mostly just because it allows you to really see how this impulse momentum theorem works. So this problem says a 500 kilogram sled is coasting at 20 meters per second. Out of nowhere, it turns on its rocket engines for 5 seconds with a thrust of 1,000 newtons. So the question then asks, what is its final speed? So this is an impulse momentum theorem problem. J is equal to delta P. You deliver an impulse, you change the momentum. Well, at this point, let's go back to the equation here. Notice that impulse could be F average delta T, it could be P final minus P initial, it could even be area under a curve. So there's numerous ways in which you could try to solve this equation. But we don't have a graph. So, area isn't really an option for us here. So we're going to want to figure out how we can make this work. And let's do that. We are given a force and a time. So impulse is F average delta t. And we know delta P means P final minus P initial, or MV final minus MV initial. So impulse is F average delta T. Delta P is MV final minus MV initial. So this is kind of like the real form of this equation. J equals delta P, sure, but in terms of everything else, we have F average delta T equals MV final minus MV initial. So if we are trying to solve for the final velocity, in other words, this V final here, that means if we are to do so, we need to know everything else in the equation. Do we know the average force? Well, yes, we have 1,000 newtons. Do we know the time it takes? Yes, 5 seconds. Do we know the mass? We do. And do we know the initial velocity? We do indeed. So we have everything we need in this full form of the equation in order to actually solve it. So at this point, it's really just an algebra problem. We need to solve for V final. I'll show you 2 steps in the math here just for clarity. But first, you could factor out the mass m, or why not just right away divide everything by mass. So we have F average delta T divided by the mass equals V final minus V initial. Right, I divided all terms by mass. At this point, it's probably really clear as to what to do. We're looking for final speed. Right now it's final speed minus initial speed, so we simply add it to the other side. This gives us V final equals V initial plus F average delta T divided by the mass. So I really like this equation because it gives us the initial velocity and then plus something extra based on how much force there is and for how long that force is applied. So we just need to plug in our numbers and solve. The initial velocity is 20 meters per second. The average force is the force of the thrust of the engines, which is 1,000 newtons. That engine is turned on for 5 seconds. And the mass is 500 kilograms. You should actually be able to do this in your head, perhaps. So we have 1,000 times 5, which is 5,000. 5,000 divided by 500 is 10. 20 plus 10 is 30. 30 meters per second. In other words, its velocity increased by 10 meters per second due to the rocket being turned on. Okay, so there's another example using this impulse momentum theorem. So at this point, let us go ahead and conclude the lecture with a couple end of lecture questions before we hop into the next lecture, which is conservation of momentum. So here is question number 1. It says the 2 graphs shown show 2 smooth force versus time graphs for collisions. Which of the 2 delivers the greater impulse? Okay, well remember, impulse is defined as the area of your curve. So we could find the impulse by simply finding the area of these shapes. For this one, we have 300 times 5 milliseconds. I'll just write 300 times 5 for now. And then over here, we have 150 times 10. I used a different multiplication symbol for each one, but you get the idea. So 150 times 10, or 300 times 5. Well, 150 times 10 is 1,500. 300 times 5 is also 1,500. They are the same. The answer is C. The areas are the same. One is taller but skinnier. The other one is flatter but wider. They are the same area. So they deliver the same impulse. All right, question 2. You're given a picture, and so it says the cart's change in momentum, delta P, is what? Okay. Well, in this case, we need to do a small calculation. So I'll just do this here. Delta P means P final minus P initial. So in this case, the final momentum is the one down here, 1 meter per second to the right. Actually, let me write this out in full. mv final minus v initial. So the mass is 10. V final is 1 minus the initial velocity. Be careful. It is moving to the left. So it's a negative in the equation, but it's also a negative 2 meters per second. Right? It's negative. So it's 1 minus negative 2, which is 3. 10 times 3 is 30. So the answer is a change of 30 kilogram meters per second for your change in momentum. Be careful with negatives. That's the main reason I threw this one in at the end, is to just alert you to the fact that you have to take into account direction. It is a vector. Right is positive, left is negative. Keep that in mind. All right, well, that is it for this lecture. We're going to now shift gears and talk about conservation of momentum, one of the most important topics we have with this unit. But until then, thanks for watching and have a great day.